Hello. Thought I'd make a little video to help you out here with some exponentials. So here's a little warm-up question, basically some exponent laws. Um, the main idea is with these is you're going to look at for the base of each piece, and you realize that there's actually a common base, and there often will be when we're starting off, and it's got to be 3, right? Because 3 to the 4 is 81, 3 to the 3 is 27, and down on the bottom there, 3 to the negative 2 makes 1 over 9. Because remember, negative exponents make reciprocals. So once you do this and you distribute the coefficients on each exponent, you realize that you actually have common bases all the way through, which allows you to use the exponent laws that you've known, since grade 8 or 9. And what you can do is basically, if you're multiplying, you're going to end up adding. So and if you're dividing, you're subtracting. So on the top there, the 8x and the negative 3x, I'm going to essentially collect like terms. I'm adding because I'm actually multiplying here. So 8x and negative 3x makes 5x, and then negative 20 and 3 adds up to negative 17. Now, watch out, this one has negatives down in the bottom, so you're actually subtracting a negative. So we're going to add 5x and 8x. And same thing with the negative 6 down there. So that's our final answer. We've simplified the expression as best we can, and now we just are left with a single base 3. So what this leads into is actually solving equations, and the equation I've got here has common bases. You can probably tell if you look at it a little bit, that's 5 squared, and that's actually 5 to the negative 4 on the right side, so the common base is 5. So once you rewrite it, it's I think fairly obvious that the exponents have to end up equaling each other because the bases are the same. Now later what we'll do is you'll end up taking the logarithm of both sides. So I'm going to do that here just as a preview. And it allows you to use something called the power rule, which means you can bring down those powers and they become coefficients. When you bring down the exponents, they become coefficients on the log. Now, what that basically allows you to do is get rid of the log 5s, and you're left with exponent on the left equals exponent on the right. So we could have done that from line 2, and really what we're doing though is we're dividing log 5 by log 5, which makes 1. So now you're left with kind of a grade 8 or 9 algebra problem. You solve for x, and you'll have negative 5 over 4 in the end. So we'll come back to this. We're going to check our work in a bit, but first we should look at what a graph of an exponential function looks like. So probably seen these on the news a little bit lately. We'll start with a base 3, so kind of like a tripling function. So at the beginning, when x is 0, you just have 1 unit of something. But that's because, anything to the power of 0 makes a 1. So as you plug in more x values, you can see that the y values start to increase, right? And if you put negatives in, you will get fractions. So as you go to the right, it grows taller, and as you go to the left, it gets smaller and smaller, but it'll never quite reach 0 for reasons we've seen before. Realize that you can never really get a negative y value with this function. So we know we have a name for this. We call this a horizontal asymptote. Right? And it's at y equals 0. And yeah, we saw that with rational functions and in trigonometry a little bit, which tells us we know the range then is basically everything above 0. Right? And the domain can actually be essentially all real numbers because there's no restriction on what you can throw in to the exponent in this case. So I thought it would be interesting just to compare this to another graph and just do a simple transformation. I'm going to do y equals 3 to the negative x. So what you'll see is essentially a reflection over the y-axis. It's going to take all your x values and it's going to switch the signs. So you're going to get a reflection. It's going to look something like this. So generally when you have negatives on your exponents, they should look like that. Which should maybe kind of resemble some kind of a decay function, which you might know from, say, a science course. And it has the same horizontal asymptote, same domain and range. So the reason I wanted to look at the graph is that it's a good way to check if you did your solving correctly with this equation. So I'm going to use Desmos to help me check this. So just give me a second. I'm going to switch over. And I'm going to plot each one of these, and I need to have the exponent. It wants brackets. Took me a couple tries to realize what was going on there. I wasn't looking carefully. Yeah, so I need brackets 2x minus 1. There's my first function. And the other one, because it has a fraction for its base, it's actually going to go the opposite way. So it looks something like that. So what I want to try to check is if they actually cross at -5/4 like my algebra showed. So right now I'm looking in the wrong spot. I need to be a little bit more to the left, because -5/4 is actually like negative, not 1.2, but it's around -1.25. So I should be a little bit further left. And then I can zoom in and I can try to tell if the blue and green functions actually cross each other at that spot. So it's hard to see because they're so close to the axis. They're running along asymptotes there. So if I kind of zoom out, I can see a point. It looks like they're actually crossing right on the axis, but that's just a quirk of Desmos because it's rounding. If you zoom in, you realize that it's not actually at 0. And it does look like they share that x value of -1.25. So the confirmation that our algebra was correct. It's not super clear because the graphs are pretty flat in that spot. But why I thought it would be good is that you can see like the blue graph, the positive exponent, and the green graph with the fractional base actually has a negative exponent because 1/625 is 5 to the -4 actually. So that was our little check. We can tell there is an intersection point there. Thanks for watching. Now get practicing. Have fun.